Hello and welcome to this video on the solving of compound inequalities involving the word and. Notice and in quotation marks here. So a compound inequality is a collection of two or more inequalities that are considered at the same time, considered together, and they're connected by some special words, either the word and or the word or. I will have a video in the future coming up where we talk about solving compound inequalities involving the word or. This video here is specifically examples involving the word and. Okay, so let me begin. I just have several examples, and we'll talk about what the word and means and how we're going to solve these compound inequalities. Alright, so the first example I have, and again all five of my examples in this video today, I'm going to be asked to do the same thing, which is the following. Solve each compound inequality and then express the solutions to the compound inequality using set builder notation and interval notation. And we're also asked to graph the solution set, and that means draw a picture of all the solutions on the real number line. All right, there's only one variable involved here, so just one number line. So my inequality for the first example is 2x plus 1 is greater than or equal to 5, and notice this connecting word, and negative 3x plus 2 is less than 5. So when you see the word and connecting two inequalities, making a compound inequality, what you're looking for, the solutions are real numbers, or I'll just say numbers, that satisfy both inequalities. So numbers that make this inequality a true statement and at the same time make this inequality a true statement as well. So solutions here are numbers that make both inequalities true. Alright, so that's what you're going to be looking for when you see the word and making a compound inequality. Alright, so I'll have here are the steps we're going to follow. So first, we solve each inequality separately. Alright, I'll find the solutions to this first inequality and all the solutions to this second inequality. Alright, we'll do that separately. So solve each inequality separately. Okay, so I'll do that here in this little space, and I'll bring a second page in when we run out of room. Alright, so this inequality I'll do in this orange color. So we have 2x plus 1 is greater than or equal to 5, right? And I'm trying to find the numbers that I can replace x with to make this a true statement. And solving it's a linear inequality, right? This is x to the first power. Solving a linear inequality is really not that much different than solving a linear equation. I'm going to gather all the terms with the variable on one side and terms without that variable on the other. You just have to be careful, you have to know when the direction of the inequality symbol changes, and that only changes, that's really the only thing you're going to have to worry about, is when you multiply or divide both sides by a negative number. Alright, there are other cases too, but that's really the main thing we're going to worry about. Am I ever multiplying or dividing both sides by a negative number? If you're not doing that, if you're just adding or subtracting, or multiplying by a positive number, the inequality symbol stays the way it is. It keeps its same direction. So the first thing I would do here is subtract 1 from both sides, right? Get all the terms with x on one side, terms without x on the other. And this is just subtraction. So the direction of the inequality will stay the same. So I'll still have, I'll have 2x on the left is greater than or equal to, same symbol, and 5 minus 1, 4 on the right. And then to get x by itself, to solve for solve the inequality for x, I divide by 2 or multiply by a half. Right, same thing. Now this is a positive 2 that I'm dividing by. So again, the inequality symbol does not change direction. It will stay the same. So we have x on the left side still is greater than or equal to, and then 4 divided by 2 is positive 2 on the right. Okay. So the solutions of this first inequality are any number x. I can replace x with anything greater than 2. So like 3, 4, 5, 6, 2.5, 2.1, anything greater than 2 will work, and or equal to 2, right? The or equal to, so 2 works as well. And then, so here's the solution set for this first inequality. I'll call it solution set 1. And just for brevity, to keep it short, I'm going to call this first set set A. All right. So the solutions of this first inequality are all values x such that x is greater than or equal to 2. All right, and this the way I've written this set here is what they call set builder notation. I've discussed this in previous videos. If you've been watching, fine. If not, look up videos on set builder notation. I'm sure you'll find something to help you a little more. I'm going to kind of glance over that right now. All right, so that's the first inequality. All right, then I'm going to solve the other inequality, right? This is still on step 1 here. Maybe I should have written steps. Let's do that now. So there's steps involved in solving a compound inequality with the word "and" in it. All right, the next one, I'm going to solve the other inequality. Negative 3x plus 2 is less than 5, right? Just less than. All right, and solve it just like any other linear inequality. I'm going to have to subtract 2 first. And that is just subtraction. Addition or subtraction does not change the direction of the inequality. So we have negative 3x on the left is less than, same symbol, and 5 minus 2 is positive 3 on the right. And then I want 1x, not negative 3x, so I'm going to divide by negative 3. All right, divide by negative 3. Now here's where you got to be careful. Yes, the left side is 1x. The right side, 3 divided by negative 3, is negative 1. But here's the case I mentioned earlier. I talked about, the only thing you're really going to have to worry about, if you multiply or divide by both sides by a negative number, which I have done here. I've divided both sides by negative 3. The direction of the inequality flips. So instead of is less than, that flips over and becomes is greater than. All right. So here are the solutions. X is alone now. Here are the solutions to the second inequality in this compound inequality. So this statement, this second inequality, will be true when I replace x with any number greater than negative 1. So 0, 1, 2 would all work. Negative 0.5, negative 0.2, 1.3. Any value greater than negative 1 will work in this inequality. We'll make that a true statement. But not negative 1 itself, right? Notice its number is just greater than negative 1, but not equal to negative 1. All right, and so I'm going to call this our solution set number 2. I'm just going to call for, again, for shortness, just so I don't have to do a lot of writing, call it set B. And this set B, right, the solutions of this second inequality are all values of x such that, a little bar, and then all the values of x such that x is greater than -1. All right. So I've done the first part. All right. We've solved each inequality separately. The second part in solving a compound inequality involving the word and. You may have, again, if you saw my video previously to this on finding the intersection or the union of two sets, because that's what I have here are two sets, set A and B. I have two sets of solutions to each of these inequalities, and we're connecting them by the word and. If you watch that video I put up on intersections, when you see the word and, you should immediately be thinking of the intersection of two sets. So then we're going to find the intersection of the solution sets. Alright, so again, what the intersection was, and I'm not going to go that in depth here, right? I did put up a previous video on finding the intersection of two sets. All you're looking for now are exactly what I set up here. We're looking for numbers that are, making both inequalities true. We're looking for numbers that are in both of the solution sets. Alright, now the symbolism for this, right, if you again recall from my video on intersections, when I'm saying find the intersection, I have set A there, the solutions of that first inequality, and then intersected with, right, a little upside down U symbol, and then set B, right, the solutions of the second set. Okay? Or you could write A and B. This symbol is just a set notation symbol for the word and. Alright, so let me do that down here. So I'll keep these sets up. Alright, there's the one inequality and its solutions. There's the other inequality and the compound inequality and its solutions. Alright, and then let's take a look at their intersection. Alright, so here's a number line for you. I like to draw pictures of these things. Alright, so here's a real number line where I'll draw a picture of each of these sets. Alright, so again, this represents the real numbers, and 0 somewhere, and then positives to the right, negatives to the left. And if a number on this line is to the left of another number, numbers on the left are considered smaller than the numbers to the right of them. Just remember that. Considered less, and numbers to the right are considered greater. Alright, so I did set the solutions of that first inequality in orange. So I'm going to put that picture in orange on my number line. So all the numbers greater than or equal to 2. Alright, so 2 would be to the right of 0. There's 2. Now, remember, every number greater than 2 and 2 itself, right? Every number greater than 2 or equal to 2 is a solution, is part of set A. So 2 itself is a solution of that first inequality. I'm going to indicate that with a nice solid dot, a solid point to indicate that yes, 2 is a solution to that first inequality. And then all the numbers greater than 2. Right, all the numbers greater than 2, which are 3, 4, 5, all the numbers to the right of 2. So here's a picture of set A. And I'll put A next to it. All the solutions of that first inequality. Alright, then for the second inequality, where I did it in this light green color, I'll do the same thing. I'll do it below. The solutions of the second inequality are all the real numbers greater than -1. So where's -1? That would be to the left of 0, right? That's less than 0. Notice it's though all the numbers greater than -1, but not equal to -1. So below here, I'll put below -1, this nice open point, like a hole, indicating that -1 is not a solution -1 does not belong to this set I called B, the solutions of this second inequality. But then all the other numbers, all the numbers greater than -1, so 0, 1, 2, 3, all the numbers to the right of it. So all these numbers, all the way to the right forever, all the numbers greater than -1, these are all the numbers that belong to set B, all the solutions of that second inequality. All right. And then what I'm trying to find is, again, the intersection of A and B. What numbers are solutions of the first inequality and, right, the word and was there, the second inequality. All right, so if we take a look at this picture, obviously -1 isn't because it isn't in B. All of the numbers up until 2, right here, -1 up to 2, these are all in set B, but not in set A, so they are not in this intersection. It's all of these numbers here, right? All the numbers where there's overlap, and this goes this way forever, right? All of these numbers are in the intersection. All right. So, and then is 2 in the intersection? Let's see. 2 is in A, yes. 2 is also in B, right? You got the number 2 right there. So 2 belongs to the intersection, and every number greater than 2. Right? So the intersection has all numbers greater than or equal to 2. I'll write it in words first, and then we'll go through and do all the other stuff that was asked of us. Expressing the solutions of the compound inequality using set builder notation, interval notation, and making a graph. So the intersection has all the numbers greater than or equal to 2. Great. All right, so let's make a graph of this. All right, so I'll pull this up. So the graph of the solutions to this compound inequality, right, this one we started with, I have the real number line. There's 0. And as we said here, all the numbers that make both of these true, this inequality and this inequality, are just the numbers greater than or equal to 2. All right, and so here those are. Here's the number 2, right? It's to the right of 0. We have 2 is in the set, right? 2 is in the intersection. And also all the numbers greater than 2. Right? So to the right there, all those numbers are in the intersection as well. Great, so there's part 1. They asked me, I like to make the graph first. Then we were asked to write the solutions in what's called set builder notation. So that's what is the intersection, what is this A intersect B, and this is set builder notation, like what I have over here for set B. All right, this is called set builder notation. So the solutions of this inequality, right, this compound inequality that we started with the 2x plus 1 is greater than or equal to 5 and -3x plus 2 is less than 5. Well, the variable's x in there, so the solutions are all values of x, all real numbers x such that, little bar, and then the conditions, all real numbers x such that x is greater than or equal to 2. As we see in my graph here, right? All the numbers are in this little picture up here. And try it out. Take a number 2 or greater, plug it in here, and see if both are true. So let's test one out. How about 3? 3 is in this, right? 2 times 3 is 6, plus 1 is 7. Is 7 greater than or equal to 5? Yes. And then -3 times 3 is -9. -9 plus 2 is -7. Is -7 less than 5? Yes. So again, all the numbers in here, or all these numbers here, 2 or greater, make both of these true. This one and this one. All right. And then finally, They ask us to write the solutions in what's called interval notation. So I'll just write, we're writing an interval down here. And again, if you've seen other videos of mine, you can see how to write, sets of numbers in interval notation. I'm not going to go that much in depth here. Please look up videos on interval notation if you're unfamiliar with it. Hopefully you're not by now, though, if you've seen my videos up to this. So interval notation, we're describing the same set. It's gonna mean the same thing as this set here and this picture here. So we go low to high, and look at the set of solutions. That's this set, this little part of the picture here. And there's only one piece to it, right? There's no gap in it. There's no hole in it anywhere. It's all one big piece to the right, moving to the right forever. Is there a left end? Yes, and this left end is at 2, so I put 2, comma. And then is there a right end? Well, the arrow here indicates that it goes this way forever. So to indicate that there's no right end, no largest value in this set, we put a infinity symbol, right, to indicate that this goes this way infinitely great, it gets infinitely large. And that's, that's not a number, right? Infinity is not a number, it's just a concept, an idea. And then we cap these off with either a parenthesis or a square bracket, a rectangular bracket, depending on whether or not those endpoints actually belong to the set. So how about the number 2? Well, we've seen that 2 is actually in this set. 2 is a solution to this compound inequality. It makes both of these true. So to indicate that 2 is a solution, I put the rectangular bracket. All right, little 90-degree angles here. That tells me that 2 is part of the set. And then all the numbers greater than 2, up to infinity. Now, infinity is not a number. I mentioned that already. And because it is not a number, it is not actually a number in the set. So I'm going to put a parenthesis around that. Parentheses mean that the number on the end is not in the set. Infinity is not a number, so it can't be actually part of the set. Wonderful. So all these here, all of these in this box, all 3 of these, mean the same thing. They represent the same set of numbers, all the numbers 2 and greater. And all those numbers, 2 or greater, pick any one you want, make both of these inequalities true, this one and this one. All right, satisfy this compound inequality. All right, so the steps again are, we solve each inequality separately. Think of those solution sets to each inequality. And then find the intersection of those solution sets. Find the overlap. What numbers satisfy both or are in both solution sets. Okay, so that's all I'm going to be doing for the rest of this video. Alright, so my next examples, they're all the same. Alright, it's just the solutions might end up different. It's not always going to be the numbers 2 or greater, that make a compound inequality true. So here's another compound inequality. 4x minus 5 is less than 7. And, alright, again the key word being and, 3x minus 1 is greater than negative 10. Alright, so like I did in the last one, right, is solve each inequality separately. Alright, so I'll do the first one in a little light blue here. I'd be adding 5 to both sides. Alright, and then that gives me 4 times x on the left is less than 12 on the right. And then dividing both sides by positive 4. Alright, division by a positive number doesn't change the symbol. I'm getting x is less than 3. Alright, so I'll call this again set A for my set of solutions to the first inequality. That's all the values of x that are less than 3, such that x is less than 3. Right? So there's the set of the solutions of the first inequality. Right, and I do the same for the next inequality. And we have 3x minus 1 is greater than negative 10. I'd be adding 1 to both sides first, leaving me with 3x on the left. And that's just addition, so greater than still. And then negative 10 plus 1 is negative 9. And then we would be dividing by positive 3. And that is a positive 3 that we're dividing by. So again, the inequality symbol does not change. That's x on the left is greater than, and then negative 9 divided by 3 is negative 3 on the right. And again, I'll call this set B. Right? B is the set of all the solutions of this second inequality, which are all values of x such that x is greater than negative 3. All right. So again, the solutions of the compound inequality, the solutions of the whole thing, are the set A intersected with B. All right. And we can determine what those are here in a second. Now what I'm going to do is I'm going to draw a little picture. You can probably figure it out just by looking at them. But I'm going to just draw a little picture. Here's a number line, and there's the number 0, and I'll put up the numbers that are in set A. The solutions of this first inequality are the numbers less than 3. All right, so 3 is over here. The number's less than 3, but not 3 itself. Right? Just the number's less than 3. So I put a little open point, a little hole above 3. Not 3 itself, but all the numbers less than 3. 2 is less than 3, 1, 0, that's going this way forever. So there's set A, the solutions of the first inequality. Then set B, all the numbers greater than negative 3. Well, negative 3 is over on this side of 0. Right, negative 3 will be over here. All the numbers greater than negative 3 are solutions of the second inequality, but not negative 3 itself. So below there, I put a little hole, right? Negative 3 is not in this set. And then all the numbers greater than negative 3 are over this way, right? Negative 2, negative 1, 0, 1, 2. All those numbers are greater than negative 3. There's set B. Right? And what we're looking for, again, is the intersection. A intersect B. What numbers are in both A and B? What numbers satisfy both of these inequalities at the same time? Well, hopefully you can see where the overlap is. That would be all these numbers in here. Between negative 3 and positive 3. All right, all the numbers between negative 3 and positive 3. But not negative 3 itself. Right? Negative 3, yeah, negative 3 is in set A, right? There it is there. But negative 3 is not in set B. So negative 3 does not belong to the intersection. Same thing for positive 3. Yeah, positive 3 is in set B. There it is, right, on that little part of the graph there. But positive 3 is not in set A, so it doesn't belong to the intersection. So you could write it out in words to say all the numbers between negative 3 and positive 3, right, just not including negative 3 and positive 3. All right, so I'm going to write that out in set builder notation. All right, so the solutions of this inequality, this compound inequality, are all values x such that, now again, we can just say simply x is less than 3 and use our word and there. Just use the solution. X is less than 3 and x is greater than negative 3. All right. This is all well and good. This is great. You can write it this way. This means these numbers, right? The numbers that are both less than 3 and greater than negative 3 at the same time. Right? That's all the numbers between negative 3 and 3. But another way I could write this, and I'll make a video after this as well, going into this in more detail. But if I have an overlap where I'm between two numbers, another way to write between two numbers is to connect two inequalities. So I could also say, or do this, say A intersect B, or the solutions of this inequality are all the values between negative 3 and positive 3. So one way to write that is like this also, with this connected, where I connect these two and make a single inequality with two inequality symbols. See how this is x is greater than negative 3 if you read it from right to left. X is greater than negative 3, and at the same time x is less than 3. This is a way to say that x is between negative 3 and positive 3. All right, great. So there's one part of our solution. Right, here's the set builder notation. Let me make the graph. All right, I'll make the graph as well. All right, so there's one part of our solution. I'll put in a box. Right, you could do either or, right, either this or this. Here's the graph of our solutions. All right, so again, I have the real number line. throw 0 somewhere. And all the numbers that make this compound inequality true, right? All the numbers that make our original compound inequality, both of these a true statement, are these numbers between -3 and 3. So here's -3 over here, +3 over here, and it's all the numbers in between, but just not including the ends, right? We said a second ago, right? -3 is not in both sets. 3 is not in both sets, but every number in between is. So there's our picture right here. Just all the numbers in between -3 and 3. All right, and then finally, for our interval, all right, write the solution, the same set, this picture, all these represent the same set of numbers. For our interval, again, there's only one piece of the graph here, right? This picture only has one piece to it. There's not another piece over here or another piece of the graph over here. This is one piece, so I'm going to write one interval. And what is the left end? The left end is at -3, so I put -3, comma. And then going through it, what is the right end? The right end, or the high end, is at +3. And then we said a minute ago, right, -3, +3 are not in the set, so parentheses on both of those, right? -3 is not in the intersection, +3 is not in the intersection. All right, so here's the final piece of what they asked for. All right. So this little interval here from this is representing all the numbers between -3 and 3. This graph represents all the numbers between -3 and 3. This statement up here, this set builder notation, represents all the numbers between -3 and 3. All three of these things mean the same thing. And they're all representative of the solutions of this compound inequality. And if you want to test it out, pick a number in here. How about 0 or 1 or 2 or 1.5 or 0.3 or -0.75? Just take any number between -3 and 3 and plug it in for x, and you will see that both of these inequalities are true. All right, so I'll do a simple one out loud. How about just 0? All right, 0 is between -3 and 3. Well, if you put in 0 here, 4 times 0 is 0, minus 5 is -5. Is -5 less than 7? Yes. Then 3 times 0 minus 1 would be -1. Is -1 greater than -10? Yes, right, because -1 is to the right of -10 on the number line. So yes, both are true when x is 0. And again, try it out yourself, and there's infinitely many numbers in here. Go ahead and pick a few. 1, 2, -1, -2, -1.5. Like I said, anything you want, as long as it's between -3 and 3, will satisfy both this inequality and this inequality, therefore the whole compound inequality. Wonderful. All right, so let's just keep doing this. Right. So the next example I have is yet another compound inequality involving the word and, where the two inequalities are connected by and. All right, and as before, I'm going to solve each of them separately, and then we'll find the intersection. And when you see and, you think intersection. We'll find the intersection of the solution sets. All right, so first, this inequality here. Subtract 3 from both sides, and I have -8x is less than -8, and -5 minus 3. And then divide both sides by -8 to get x alone. Now, again, here's the tricky part. I divided, right? If you multiply or divide both sides of an inequality by a negative number, it flips the symbol. The direction of the inequality changes. So we have x on the left is greater than, and then -8 divided by -8 is +1. All right, so again, I'll call this set A. All right, the solution set of this first inequality is all values of x, as long as x is greater than 1. Great. All right, then the other inequality, I'll again do in a different color. Now you could get rid of the fraction denominator here by multiplying everything by 3. I'll just leave it this way for now. I'm going to subtract 1 from both sides. We get 2/3 times x, and then I only subtracted. Adding and subtracting doesn't change the inequality symbol, doesn't change the direction. So still is less than, and then 3 minus 1 is 2. and then I would divide by 2/3. Now division, remember, is the same as multiplication by the reciprocal. So that's the same as multiplying both sides by 3/2. All right, I'll do the same thing over here. So the 2's canceling over here, 3's over here. You got left with 1x, and that I multiply both sides by positive 3/2, so that doesn't change the direction of the inequality. So it still is less than. And then over here the 2's cancel, I'm left with just 3. All right. So I'll call this set B again. All right, and it's the set of all numbers that are, less than 3. These are all the solutions of that second inequality. All right, and then I'm seeing the word "and" here. So the solutions of this compound inequality, solutions of the whole thing, are the intersection, right? A intersect B, right? Which I'll write over here in set builder notation after we take a look at a little picture. Right, now again, if you see it, fine, but here's a little picture. All right, here's the real number line. Got 0 somewhere. And I did light blue for A, right? So all the solutions of this first inequality are, greater than 1, but not equal to 1, right? So 1's here to the right of 0. 1 is not a solution of that first inequality, right? So I put a little open point above it. And then all the numbers greater than 1. So all these numbers here, 2, 3, 4, 5, forever. All right, so that's set A. And then set B, the solutions of all this, this second inequality. All the numbers less than 3. Now 3 would be to the right of 1 on the number line. And notice it's all the numbers less than 3, but not equal to 3. So 3 is not a solution. Right? Again, so a little open point here below 3. And then all the numbers less than 3. That's 2, 1, 0. That's this way forever. So there's set B. All right, and we're looking for the intersection, right? The overlap. What numbers make both this inequality and this inequality true at the same time? And hopefully you can see it's these numbers here, just the numbers in between 1 and 3, right? To the right of 3, those belong to A but not to B. To the left of 1, those belong to B but not to A. 1 itself, 1 doesn't belong to A, so it won't belong to the intersection. Same thing for 3. 3 does not belong to B, so it won't belong to the intersection. So if I write the set builder notation here, the solutions of my compound inequality, this thing here, are all the numbers that are, greater than 1. I'll just write the inequalities as is with the word "and." X is greater than 1, and X is less than 3. All right. Again, you could also write this, right? Because there's this betweenness, right? Like in my previous example, notice how all my solutions are between two numbers. Well, if you have that case, if you have ever run into the case where all the solutions are between two numbers, you can actually make these two inequalities into one connected inequality, like I did in the last example. So I could write this as well. All the solutions are values of x such that x is between 1 and 3, right? With this little connected, one inequality statement with two inequality symbols. These mean the same thing. X is greater than 1, and at the same time x is less than 3. This means the same thing. You see how x is greater than 1 if you read this from right to left. X is greater than 1, and at the same time x is less than 3, meaning that x is between 1 and 3. All right, so both of these are totally fine. This is a way to write the solutions of this compound inequality in set builder notation. Alrighty, and then we'll get to the graph and the interval. All right. So now it's just, we'll draw the graph of the solutions of this compound inequality. Right, here's our real number line. Right, there's 0, and the number 1 is to the right of 0, the number 3 is to the right of 1, and the solutions to our compound inequality are all the numbers between 1 and 3, or all the numbers greater than 1 and at the same time less than 3. That's all of these numbers right here that I'm marking in orange, right? Notice the holes on 1 and 3, right? 1 is not in the set, 3 is not in the set, but all the numbers in between are. All right, so 1.5, 2.5, 2, 2.3, 2.79, 2.99, 1.001. Any number between 1 and 3 is fine. And then for the interval, right, just like our last example, right, there's only, in my picture here, there's only one piece of this graph, right? There's not another part of it over here. There's not another part of it over here. There's just this one piece of the graph. So I'm just going to write one interval, and it's, in this piece, the left end is at the number 1, comma. The right end is at the number 3. And then this left end number and right end number are not part of the set. They're not solutions of the compound inequality. So again, I indicate that with parentheses. Right. So this example was very similar to the last one. I just had a fraction involved, right? There was this 2/3 here. That's really the only major difference between this example and the previous one. And just double check if you want, to just see if you believe this. Pick any number you want between 1 and 3. Like I said, 2. How about 2, right? Now it doesn't have to be 2, right? It can be any real number between 1 and 3. Like the square root of 2, that's about 1.4. The square root of 3 is about 1.7, and so on, right? You can pick a lot of numbers in here. But let's say 2. I'll just take 2. Is 2 a solution of the compound inequality? Does it make both of these true? Let's double check. Negative 8 times 2 is negative 16, plus 3 would be negative 13. Is negative 13 less than negative 5? Yes. Yes, it is. It's to the left on the number line, right? And 2/3 times 2 would be 4/3, right? 2/3 times 2 over 1 would be 4 over 3. 4/3 plus 1, need a common denominator. 4/3 plus 3/3 is 7/3, which, if you put it as a mixed number, 7/3 would be 2 1/3. Is 2 1/3 or 7/3 less than 3? Yes, it is. So 2 makes both this inequality and this inequality true. It is a solution of the compound inequality. And you can do that again with any number you want. Plug in, 1.879, plug in 2.993, whatever you want. As long as it's between 1 and 3, it should make both of these inequalities true at the same time. All right, so let's keep going. Might come into a different type of scenario. These last two examples are pretty similar. Let's see if we can come across any scenarios that are a little different. All right, so I have here another one, another compound inequality, where the connecting word is and. So we're looking for numbers that make both this inequality and this inequality true at the same time. All right, so the first one was, the first step was to solve each inequality individually. So this one here, I would have to add 5 to both sides, and that's just addition, so the inequality direction won't change. I'll have 3 times x is less than negative 3, right? Negative 8 plus 5. And then I would have to divide by positive 3, and that is a positive 3 that I'm dividing by, so again, the inequality direction will not change. X is less than, and then negative 3 divided by positive 3 is negative 1. All right, so I'm going to call this again set A. Is the set of all the solutions of this first inequality. It's all the numbers such that, that are less than negative 1, right? Such that x is less than negative 1. Okay, so there's the set of all the solutions of that first inequality. I'll do the same for the second one, right? 2x plus 1 is greater than 5. I would first subtract 1 from both sides. Now that's just subtraction. That's not multiplication by a negative or division by a negative. Addition or subtraction, the inequality symbol will not change direction. So this is still 2x over here, still is greater than, and then 5 minus 1 is 4. And then I would have to divide by positive 2 on both sides. And again, this is a positive number I'm dividing by, so the inequality symbol will not change direction. So this is x on the left is greater than 4 divided by 2 is positive 2 on the right. All right, so I've set B here is this, the set of all the solutions of the second inequality, and that's all the values x such that x is greater than 2. All the numbers greater than 2 are the solutions of that second inequality. All right, so then part 2, right? Then the solutions of our compound inequality. Write it again. So the solutions of the whole thing are, what do they share? What numbers are actually making both of these true? What is in the intersection of A and B, right? So this A upside down U, B, A intersect B. All right, so before I get into that, again, if you see it, great. But I like to draw little pictures, you know that by now, right? So here's a number line, real number line with 0 somewhere. The solutions for the first inequality are all the numbers less than -1. Now -1 would be to the left of 0. Notice it's all the numbers less than -1, but not equal, not -1 itself, so a big hole above -1. And then all the numbers less than -1 are that way, -2, -3, -4, and so on. So there's set A. Right. And set B is all the numbers greater than 2. Right. So all the numbers greater than 2. So 2 is over here to the right of 0. And notice it's all the numbers greater than 2, but not equal to 2. So 2 is not included, 2 is not in the set, and all the numbers greater than 2, 3, 4, 5, are to the right. So there's B. Now look at these pictures and ask, is there any number that's in both? Is there any overlap between these two pictures? I'm not seeing any. All the numbers in A, none of those numbers are in B, right? All the numbers in B, none of those numbers are in A. There's no overlap here. And what does that mean? Well, that means that the intersection has no numbers in it. So a way to indicate that is by drawing just a simple empty set of braces, all right? A little brace, another little brace with nothing in between. And this symbolism here is referred to as the empty set. Right. So that means that there's no solution. Right? That means no number, there's no number out there that satisfies this inequality and at the same time this one. All right, so you might see the empty set written, the set with nothing in it, as just an empty set of braces like this. Or you might also see the empty set drawn as like this circle, a 0 with like a slash through it, almost like a no smoking sign type thing. So either one of these symbols you might see, just an empty set of braces or this circle with the slash, to represent the empty set, meaning that there is no solution to this compound inequality. So then if you were to make a graph, well, if there's no solution, there's no graph. And if you're asked to make an interval, again, if there's no solution, there's nothing in the set, there's no interval to write, right? An interval will represent like infinitely many numbers, right? We've seen our intervals in the past. The last one had the interval, from 1 to 3, right? This one here. You'll write an interval when there are actually, infinitely many solutions on the real number line to draw. So no solution will imply that there's no graph, because all a graph is a picture of solutions. And if there's no solution, there's no interval to draw either. Now you could write this as your interval. You could say the interval is like the empty set, but that's not really an interval. Okay? But yeah, so nothing, no solution, totally done with this problem. There's no number that you can think of, that I can think of, that makes both of these inequalities true at the same time. All right. So that was a little different, right? No overlap that time. And I have one final example for you. And let's see what kind of scenario happens there. All right, so same thing, same kind of example. Got a compound inequality where the connecting word is and. 5x plus 1 is less than or equal to 6, and 3x plus 2 is greater than or equal to 5. So just like the others, same steps. I'm going to solve each one individually. So let's take this first one. I have to subtract 1 from both sides first, and then I have 5x is less than or equal to 5, and then I would have to divide both sides by positive 5, so it's still x is less than or equal to 1. Alright, so again, I'm going to call this set A just like I have been. And the solutions of all, this set A is the set of all the solutions of this first inequality. It's all the numbers x such that x is less than or equal to 1, right? Positive 1. Okay. And then I've got this set, right? So I want to find the set of solutions to the second inequality. So first I'd be subtracting 2, right, leaving me with 3x on the left is greater than or equal to 3 on the right. Then I'd be dividing both sides by positive 3, which is again positive. So I'm left with x is still greater than or equal to 1. Right? So set B, the set of the solutions to this second inequality, is all the numbers x such that that number is greater than or equal to 1. Those are all the solutions of the second inequality. Well, let's draw, again, when I have all the solutions of the first set, all the solutions of the second inequality, we're connecting them with the word and, so I'm going to try to find the intersection. All right, so one more time here, last example for you. So the solutions of the compound inequality is whatever the intersection of these two solution sets are. All right, so again, I draw a little picture. Here's the number line. There's a 0 to separate my positives and negatives. First set, light blue. All right, all the numbers less than or equal to 1. Right, so 1's here. Less than 1 or equal to 1. So this time 1 is a solution. Right, and you can try it out. Plug 1 in for x. That'll make this first inequality true. And all the numbers less than 1. So 0, negative 1, all the stuff to the left. Right. So there's set A. Right, all those numbers. And set B, all the numbers greater than or equal to 1 make the second inequality true. So greater than 1 or equal to 1. Right? So 1, and just right under 1 here, that is a solution. So a nice solid point again. And all the numbers greater than 1, so 2, 3, 4, all the numbers to the right of 1, there's set B. So where's the overlap? All right, what number is in both, or numbers are in both set A and B? What numbers satisfy both of these inequalities? Well, hopefully you can see that there's only one number, and that's the number 1. 1 is the only number that's in both sets, right? 1 is in A and it's in B. But then anything to the right of 1 is in B but not A, and anything to the left of 1 is in A but not B. So the only number is the number 1. So you could do this a couple ways where you say, hey, the intersection, A intersect B, is just draw a little set with some braces and throw the number 1 in there. That's it. That is the only number that belongs to the intersection that satisfies both of these inequalities at the same time. You could also do it with the variable too. You could say, or you could do the solutions of this compound inequality are all values of x such that x equals 1. Right? It's only one number. It's only x can only be 1. And then double check. Plug in 1 for x. 5 times 1 is 5, plus 1 is 6. Is 6 less than or equal to 6? Yes, it's equal to 6. It's got the equal part satisfied. And then 3 times 1 plus 2 that's 3 plus 2, that's 5. Is 5 greater than or equal to 5? Yeah, 5's equal to 5. So yes, the number 1 does satisfy both these inequalities at the same time, this one and this one. And that's the only one. All right, so there's my set notation, set builder notation. And then again, you could make a graph of this. All right, there is actually a solution involved. So here's a graph of the solutions of this compound inequality. So number line here, there's 0, and Here's the number 1, and that's the only solution. So I will simply put a single dot right above the number 1, and that's it. That's all I'm drawing, because that number is the only solution of our compound inequality. All right. And I guess you could make an interval for this, but usually intervals are reserved for when there are infinitely many solutions. But you could make an interval for this where there's just that one dot, there's just that one piece of the graph. So the left end of it is 1, the right end of it is 1, and then you put brackets on it. And this is silly though, right? Because again, the little rectangular braces means that 1 is a solution. 1 is a solution. And this is all the numbers, from 1 to 1. So this only represents the number 1. But usually you're not going to write this. This is kind of silly. You would probably never see an interval drawn like this. Because again, I said it a second ago, intervals are usually reserved for when there are, infinitely many solutions, or there's a nice interval, a nice range of solutions. Yeah, and so instead of seeing this, you'll most likely just see this with the curly braces and just the single number in it. All right. But still, it's not wrong, I guess, to draw an interval like that. Okay, great. All right, so you saw a lot of scenarios there, right? Compound inequalities involving the word and. We saw one where both sets of solutions were going in the same direction on the number line, and then you look for the overlap. You saw 2 examples where they were going in opposite directions, and there was a clear overlap. All the solutions were between 2 numbers, between 1 and 3, and so on. And in those cases, you could actually write a connected inequality for betweenness. Then another case where there was no overlap whatsoever, and the compound inequality had no solution, and therefore no graph, no interval. And then you had this last example here where there was overlap, but they only overlapped at 1 number. All right, and so the graph was just a single dot, and the interval would be kind of silly to write. You still can, but usually not done if it's just a single number in it. Okay. All right. So solve each inequality separately if the word and is involved, and then if the word and is involved, then find the intersection of the 2 sets. Right. Great. And as I like to say at the end of these videos, try the best you can, do the best you can to learn the material, try to understand as much of it as you can on your own before you go looking for help. I find that material tends to stick with people better. People tend to have longer recall when they've taken the time and put in the blood, sweat, and tears to learn it on their own. So read the material, of course, read the author's examples, perhaps even try to work on examples and try to solve them before you see how the author did it, and then compare your work to the author's, and maybe you can learn something from that. Work on plenty of practice problems, practice exercises, look up solutions whenever they're available so you can check your work, check yourself. Just don't give up after the first attempt at a problem, first approach. There are often many approaches to a problem that'll work. So if after several attempts at a problem, you're still not getting it, it's still not making sense, still not clicking, perhaps you should go back and read the material again, more slowly and deliberately. Take notes, maybe even a 3rd time, because after working on some problems, you'll have a better idea as to what the author is looking for from you, what the author expects of you. And so then going back and reading the material again, you'll probably catch some things that you didn't catch the first time, or things will click or make sense more on the 2nd or 3rd read-through that didn't make sense on the first read-through. But if after that, if after several read-throughs of the material and several attempts at problems, you're still not getting it, well, then it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for. So ask a teacher, a tutor, a friend, someone in your class who knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there on math subjects. Look for videos on the subject. perhaps like this one, and I assure you there are loads of videos out there that are better than mine, and probably more instructive, and you can find them with ease. But just keep at it. Just stay persistent. Keep practicing. Don't give up, and try your best to have a positive attitude as well. That's the hardest thing, I think. If you go into subjects thinking I've hated this, I've always hated this, I'm going to continue to hate it, it's boring, you're probably going to hate it, and it's going to make the learning experience that much more terrible. So try to change your attitude. Try to go in with an open mind, thinking I'm going to learn something today, I'm going to take something from this, I'm going to use it in my life, it's going to be fun, it's going to be positive. And it's amazing the difference just a little change in attitude can make, as hard as that may seem. So stay persistent, keep practicing, stay positive, and don't give up. And I'm sure you'll get it. And thank you very much for watching.